Hi again, folks. Just going to talk a little bit about what's called in Taylor and Wheeler, it's called the time stretch factor. And we're going to talk a little bit about the Lorentz geometry, which is hyperbolic and not the same thing as Euclidean geometry. So if you look at a space-time diagram like this, okay, you know that we've got the light cones looking like this. And so the set of events that have the same interval, okay? What's the interval? It's s squared is t squared minus x squared. I'll just omit the deltas for brevity here. But if you recognize this equation, it's a shape, right? It's a geometric graph. So if I graph that, it's going to look like a hyperbola, which means it's going to look like this. Whoops, not like that. It's going to look like this. Move up like that. This point down here is the lowest point on the graph, and there would be 4 of these, right? 1, 2, 3, 4. If I say that I'm going to say that the distance here from 0 to this point here, okay, call that, for example, B. That would be the proper time, right? First off, because there was no change in position, no distance traveled. But what we're interested in now is, okay, suppose that there was a different point. Maybe there's a point up here on the parabola that we are interested in. What would be the clock reading on this person's clock according to us here on Earth if they're moving with respect to us? Okay, notice they're moving with respect to us, and I mean I said here on Earth, but I could have been in a rocket and then the rocket's not moving, but Earth is. Okay, so same idea. If I say that's B, then if you notice the coordinates of this, okay, the coordinates of this, well, let's do, yeah, that's fine. The coordinates of that point are slightly greater than B on the time axis, and there's some distance on the x-axis. Well, if they are in motion with respect to us, then this leg is velocity times time. That's how far they traveled, because remember, this is constant velocity motion. The question is, what's the reading on the clock? Right? What's the reading on the clock when they're over there? Well, we're saved by the interval, right? Because the interval from here to here is still satisfying the equation of the hyperbola, which in other words is t squared minus x squared. Therefore, that must also be B. That distance is B. It doesn't look like it, but that's because I'm using a flat plane to try and describe curved geometry. This is Lorentz geometry, not Euclidean geometry. So it's hard to represent, but you just have to understand, if I'm on this hyperbola anywhere, then t squared minus x squared is going to equal B. So let's just set B equal to 1 and call it something really easy like that. And now you'd see that the interval here, say B is equal to 1. So we'll say that 1 squared is equal to t squared minus x squared, but that's nothing here. By the time I get up to here, that's going to equal, that's t squared. So this is going to now be in the frame of the stationary person. What are the coordinates of that point? Well, that point is up here, so we don't know what that time is. Let's call it like t1 squared minus v times t1, and that whole thing is also squared. That's the distance that they traveled. Okay. Therefore, if I look at the distance here, this distance b, right? I'll get that 1 squared is equal to t1 squared times 1 minus v squared. and I'll see that the time, this time that I'm interested in, is 1 divided by the square root of 1 minus v squared. Okay, so in other words, for every unit of time as measured by this person on this time axis here, that person is going, that same frame is going to measure this much time happening on a axis like this one. Say the t prime axis is going that way. We're going to measure t prime as having spacing of 1 over 1 minus v squared. Now v squared is going to be a number that's much less than 1, so this is going to be a number greater than 1, and that is copacetic with the time dilation idea that I told you last time. So if I mark out hash marks on this axis as being that, I'm going to mark out greater distances along the time axis to indicate time, because their time is dilated according to me here in the t-axis, right, in the xt frame. So this thing here is called the time stretch factor, and we actually refer to it with the symbol gamma. Like so. Alrighty. And we can calculate times and distances as in special cases using only the gamma factor. Normally, you're going to want to use the interval to calculate times and distances, because that's like always taking into account both time and distance. But if you're just wondering about a time, you're saying, oh, I'm here and a rocket flies past me at 0.5. How much slower is their clock running? Well, you can calculate it really quickly with this. Okay. So the time stretch factor actually plays a part in almost every piece of relativity, because it is how you describe the difference between frames mathematically. But also, I wanted to go back and talk about the transformations to go from one frame to another. There's a set of mathematical transformations, and I'm not really going to use these a whole bunch, but I do want to make you aware of them. They're called the Lorentz transformations, and they represent the update to the Galileo transformations. And the Galileo transformations, if you remember, are just, how do I find the distance from one frame's perspective to another frame's perspective? Well, all you got to do is subtract the distance traveled, and that would be speed times time. But the Lorentz transformation, so that's Galileo. And now Lorentz comes along and says, actually, it's gamma multiplying x minus vt. Like that. Okay, so this is a Lorentz transformation, and it tells you how x and t can be transformed from one coordinate system to another to give you a distance and a time. And you can find t prime here as well. Let me make sure I'm going to get this right. I think I am going to. It's gamma t minus vx. There we go. That's a t right there. T minus vx. So it's gamma multiplying t minus vx. That's t prime. So I can find the new coordinates by going x prime being gamma times x minus vt, and t prime being gamma times t minus vx. Now, one of the problems you run into is which one's the prime frame, which one's the non-prime frame. Easiest always to just whatever perspective you're looking from, call that the unprime frame. It's tougher when you always link the unprime frames with Earth. If you say Earth is always the unprime frame, then sometimes this gets to be a little murky to try and use. Anyways, I put these up here mostly because A lot of people use them. I don't so much use them. I don't concentrate on these a whole bunch. I prefer to spend time looking at the space-time diagrams and using the interval rather than using the Lorentz transformations. Nonetheless, they do give you the same result if you go this direction versus the interval direction. So anyways, like I said, you can check your answers with this. I would think that on the homeworks, go more into the interval and use that as your kind of go-to calculation. Alrighty, good. Hope things are going well, and I will talk to you again in another video.